Okay, hello, welcome back. Let's get started. And I'm not going to start from the beginning of this lecture. I'm going to start where I left off. But I want to review a little bit, just in case you weren't here for the first part of this, and reiterate some points. We're talking about entity relationship diagramming, and we are talking about how to build databases. A few administrative things before I get started and before I forget. Sign the roster that's going around. That's the thing you should be used to already, signing the roster. Let's see, announcement number 2 is next week I will be making the midterm public. So, what do we mean by public? It's going to be posted to my website. The midterm is a take-home exam. It is not an in-class exercise. And the midterm, I haven't decided for this particular class what we're going to do, but it's probably going to be having something to do with SQL and simple database concepts. You might have to write some SQL statements. You might have to answer some simple questions. What I want to do is make it sort of an interactive kind of practice exercise to have you kind of test out your skills instead of having like a multiple choice kind of thing or something like that. The final exam will be more of a multiple choice, and that one will be an in-class exam. So the midterm's a take-home. I'll announce it next week. I'm going to write it between this week and next week, and probably over the weekend. And you'll have 3 or 4 weeks to complete it. If we have, because I've already been asked already, if we have issues with the ITU, EMS, and error messages when you try to upload assignments, don't worry, just save it. Even though we're going to put a due date on the midterm, we won't count it late, we won't deduct, we won't hold you accountable for problems with the EMS. But we have people working on it, so I'm hoping that it's going to be fixed soon and that students will be able to upload assignments without problems. But if there is one, don't worry about it. The midterm will be due in about 3 weeks. I will also have the CSLO essay ready for you, and that will be an essay assignment, but different from the CSLOs you've experienced in the past. It'll have you write something regarding databases, essentially, or Oracle. It might actually be some sort of a research project. I haven't quite decided on it yet. But that one won't be due till the end of the class. But those items aren't available yet. They will be available next week. Questions on that midterm? You do have to show up in person to take the final exam. That one is not a take-home. But that one won't happen till the last week of April, first week in May. And we'll have the TAs send an announcement out. We will also have the TAs send an announcement out about the midterm as well. Questions? Ask for no questions. All right. All right, so last week, seems like a long time ago, I started talking about entity relationship diagramming. I talked about the concept of what it was. I showed you. Here's an example, refresh your memory, of what the entity relationship diagram looks like. That's actually kind of a confusing one, actually, I think. I've got some other ones coming up. The basic concept of I'm trying to get to that slide ahead, the 3 components. Here it is. The concept of it being the entities, the relationships, and the attributes. We are putting together this diagram so that we can design our tables. And it's not going to tell us very much outside of what belongs in which table, what should be an attribute, or a piece of a column in the table, what should be a primary key, what should be a foreign key, all of the different specifics about the database construction. And I talked about the concept of an entity type being a group of objects. In fact, if you just sat through my object orientation, an entity is an object. The objects communicate with each other. Well, the entities communicate with each other. In terms of entity relationships, they have a relationship. One contains another, works for another, has some sort of a connection, which is what we're modeling. We're looking at entity occurrences as well, meaning we're not creating new entities out of occurrences. Instead, we're creating one entity and having many different types of that same entity. Same kind of concept, actually, as I just talked about in terms of objects. We have different types of entities. We have entities with a physical existence. We have one with conceptual existence. The physical ones would be staff, property, customer, part, supplier, products. The conceptual, sales order, work experience. This is where most students actually end up with problems in terms of creating these diagrams. And at the end of this lecture, I'm going to talk about a couple of the assignments. And the issue is there's many different ways of reading a problem description. And maybe on the midterm, I'll have you do a simple entity relationship diagram to see if you understand the concept. whereby you could make, work experience, a sale, viewing, all of these conceptual things end up turning into different types of entities. And you could make, like, say, one entity that has many different concepts in it instead of 2 or 3 different entities. You might have, decisions to make as to what should be an entity, what should be an attribute of an entity. So those are kind of like the loopholes or the issues that a lot of the students would fall into when reading a description. Because what you're doing is you're taking a textual description of the database and you're drawing it out, essentially, into a diagram. And depending upon your interpretation of the description, and, given maybe language barriers, maybe given vocabulary, maybe even given conceptual knowledge of whatever is being described, you might have some background information, you might not have the background information. Depending upon all these little different factors, 2 people will not come up with the same diagram. You're going to have different diagrams that are created just because of sheer interpretation. And usually the 2 diagrams, there's no right, wrong. I mean, both of them right, or both of them might be wrong. I mean, there's no indication outside of whether or not the diagram actually represents the problem that's being described. Here we have, and then this is review again, I've already covered this part, but we have the simple binary relationship where we have 2 entities that are corresponding with each other. We have a staff and a branch. We have a box, a rectangle, that shows the entity. Most of the symbol sets, and I'll show you some symbol sets at the end of this lecture, we'll show the entity as a rectangle of some sort. So they might have different, corners or something on it, but it's going to be looking like sort of like that. And we have the relationship. So we usually start out by drawing the entities out, little boxes, and then we connect the boxes together. That's the relationship. And we have entities that might have more than one relationship with another entity or with the same entity. And we talked about that last time. And here's an example of staff that has a relationship with branch, that branch has staff. I talked about how the diagram can be read left to right, right to left, top to down, bottom to up. And we have a little arrow here that represents the direction that the creator of the diagram intended for the diagram to be read in. And you notice that it's kind of unconventional for English language because the direction is leading from right to left, which means it kind of shows you can actually implement any style you want. You don't actually have to put the arrows in. The arrows are just for syntax reasons. Because you can say branch has staff. It's kind of makes it sound better that way instead of saying staff has branch. Well, staff doesn't usually have branch. And the words that you use for the relationship might be different. Might be works for, contains, has, is a member of, is something. So we also looked at degrees of relationships. So we have the number of participating entities. Here we have 2. Their degrees of relationship are different than cardinality. So a degree of relationship is how many entities are talking to other entities. And we simply count up the number of entities and we get the degrees. And so we have the number of participating entities in the relationship. Here we have some common, 2, 3, 4. What do they look like? We've seen the 2. And that's like, and in this particular example, the binary, looking at private owner owns property for rent, 2 participating entities. And then we had 3, if you remember this part, we talked about this already as well, that staff registers client at a branch. And when we start looking at 3, you'll notice one kind of difference here. We don't have the arrow. Here we have an arrow. It says property owner owns property for rent, and the arrows. It's hard to put an arrow in that, which is why some people just leave the arrows out completely. There's no need to have an arrow in there. In any case. But here we have staff that registers a client at a branch. You're not going to see this text on the diagram either. You'll just see the diagram. In fact, the diagram will probably look a little bit more complicated than that as well. That's a simple illustration. Here's one with 4 entities. So we know the degree of the relationships because we can count up the entities. Here we have 1, 2, 3, 4. They're all connected. And some students don't like to connect them like this. Instead, they'll string them out. They have one connected to another, connected to another, connected. And that's actually different. You're saying something different than if you're saying this. Because here, when you connect them together using the diamond symbol in the middle, and it's another review item to point out, the diamond symbol is used to connect, and that's why we only really go up to about 4 Once we get past 4, it's hard to actually represent them correctly. And if you read the description for what 4 actually entails, that's a lot of participation. I mean, you've got a solicitor that arranges a bid on behalf of a buyer supported by a financial institution. That's a mouthful. Normally, we don't even write sentences like that. And if you're wondering where the sentence came from, the sentence came out of a description of somebody's business problem that they wanted you to create the database for. They said, you know, create me a database that represents the relationship. You know, I need to store information about a solicitor who arranges a bid. And this is it. Basically, the sentences that you're going to be given are going to be describing the problem. Some of the sentences that you'll be given will be duplicated by other sentences, and the relationship will be the same way. Like might say, a solicitor arranges the bid. Yeah, they arrange bids. Okay, so that's all part of the same thing. And oh, they do it at a financial institution. Okay, so what ends up happening is you start reading through the description of this particular database, and I'll show you this with the first assignment, or not the first one. I think it's the third one, but we'll take a look. And then all of a sudden, oh, it's already there. Oh, you can almost use the description as a checkoff. You know, oh yeah, we already have solicitors in there. We already have bid. And you end up kind of consolidating the concept down into the diagram. It makes a clear level of abstraction. That's a little bit easier to look at than in like 10 pages of a database description, essentially. Which is why we're doing this. It makes the abstraction a little bit easier to understand and work with. We have relationship types. We have relationships with different roles. That's all a single row. Single role. One relationship with one entity with another entity doing this, doing one single type of activity. We could have a recursive relationship. This was the staff that's also an employee, or the manager who's also a staff, with a relationship with itself. So with a recursive relationship, the relationship type where the same entity type exists, so the relationship's having it with itself, participates in more than one of the different roles. Here's the example here, the staff that supervises other staff. Oh, they're all staff. It's like a student who's a TA. He's also a student, but they're also a TA. So they have multiple relationships with the same entity, essentially. We looked at that. We also looked at the concept of there being two separate relationships between two different entities. And you would also draw this with two lines. In fact, this is how sometimes you see the double lines that go across. Normally, you're not going to see too much text on here. This is for illustrative purposes. You're not going to see these bubbles up here with the role name and the role name. That's for illustration. I'll show you at the start of the next lecture that we're going to get the continuation of this. We'll look at a real diagram, actually, and you can kind of see what's on there and what's not on there. But here we have a staff that manages a branch and a branch that has staff that's part of the branch. And we have a member of the staff, branch office manager, basically giving us the names of the roles that are associated with the relationship. So here we just have two relationships, essentially, with two entities. And I think we started talking about attributes. We got this far, I think. And an attribute describes something about the entity. So it's a property of the entity or the relationship type. So we have an attribute domain, which means the type of information that we're getting is going to be a number. It's going to be a letter. It's going to be a label. So it's a set of allowable values for one or more attributes that might be associated with it. We have simple attributes, and then we have composite attributes. And this is kind of the same thing that we get with variables, with columns. I was talking about Java earlier, not variables, data members. No, I'm talking about columns now in a database. So we have a single attribute, so that might be a single component with an independent existence, or we might have a composite, which might be, let's say, a telephone number, or we have a prefix, a suffix, area code, I don't know, all the different parts, don't quote me on this, of a telephone number. We have single valued, that would be simple and composite, as I mentioned it. Then single valued and multi-valued, which is kind of a similar concept. It holds single values, or it holds multiple values for each one of the occurrences. So we can separate it out from simple to composite to single to multi-valued, depending upon how we want to represent the data. We also have the concept of a derived attribute, which is given from other information that we might have. So the database itself is deriving the value that's going to appear in there. And it might be, if you're a student and you had the certain number of grades already accumulated, it might be a GPA. That's a derived value out of all of the different grades that you have. And I think we actually hit this as well. We talked about keys. We don't have surrogate keys on here. I'm going to talk about that a little bit later in the course. But we have a candidate key as a concept, a primary key, a composite key. I think foreign key is missing from the list. Oh, no, it's not on the next slide either. So this is just a slight example, small, incomplete example about all the different key options that we have. But this is what we're showing in the database, in the entity relationship diagram for which we're going to build the database from. So at the entity relationship diagram point, we can actually kind of see which tables are working with each other, because the entities end up turning into tables in the long run. And then once we see which tables are working together, then we can actually kind of identify what's going to be primary over here and foreign over here. And we can start labeling it on the diagram. So when we take the diagram and translate it into the table format, it saves us a lot of work, essentially, which is the only reason why we're doing this. I went through some definitions. I believe the candidate being the minimum set of attributes that uniquely identify each occurrence of the entity, the primary being a selected unique value, composite being a set of two or more attributes that are put together. We sometimes have to come up with a composite key, and students don't actually like that because it's too complicated sometimes. But composites actually are sometimes unavoidable. If you don't have a unique value, you might actually have to create one by using a combination. Like the last 4 digits of the social plus the first 4 or the last 4 digits of your characters of your first or last name or something. Or some combination of something that's going to come out with hopefully a unique key. So here we have the diagram, the ER diagram of staff and branch, entities and attributes all filled in. This particular diagram has them in the boxes. This is actually kind of like the way I want to do it. I like to do it. The colored filled in boxes are not part of the diagram. They're there for instructional purposes. They're not part of the diagram. What we actually have is a box that says staff, a box that says branch with 2 relationships with the arrows going for manage and has. And we're looking at the words PK over here for primary key that's sometimes indicated. And you're probably wondering at this point, how do we put this together? So there's packages, there's programs out there, such as SmartDraw. But SmartDraw, I believe, only has like a 7-day trial on it. There's other programs, shareware programs, open source programs. Look for something that does data modeling. Something like Visio, but if you have Visio, that'd be great. Some people have never purchased Visio. It's not free software. You're probably going to have to do some hunting, find it out. In fact, I might actually over the weekend kind of see if I can put together a partial list of what's out there right now, because the environment keeps changing. New programs come and go. SmartDraw, I used to use that for years. The only problem with that is now I think they've reduced it down to a 7-day trial, which is kind of ridiculous, or a 30-day trial or something. If you get a program that's a trial, it puts a little watermark on your diagram, that's not a problem. Don't have to worry about that. When you create your diagrams for all of the exercises that you're going to be doing, you're going to have to find something to draw. Don't do this by hand. If you want to do it by hand, you can. The only problem is it's kind of like writing a research paper by hand. You got to do it in pencil, I guess. You're going to erase it. And if you do it by hand, you'll have to scan it into a file, like an image file, which a lot of people have actually done in the past. It works out quite well if you want to do it. I'm not discouraging you. I'm just saying it might be easier, actually, to pick a program to do it in. And depending upon the program, you're going to get a different symbol set, and you're going to get a different style diagram. If you're doing it by hand, I actually recommend this technique, because you're going to put everything inside of boxes. It looks like it's all enclosed. Some of the other ones have like little bubbles that come out, so all of this stuff is attached to a bubble outside of the box, and we'll see an example of that later. Some of them have different styles. I'm saying different arrowheads, lines, slashes, a bunch of symbols. Don't worry about the symbols. I think this is where we stopped, actually. So I think this is the new information coming. So if you weren't here last week, that's all the stuff we covered. So this week, we're looking at entity types, and we're finishing up this lecture, and then we're going to learn how to translate the diagrams into a set of tables. Okay, so We only have two options with the entity types, and I think I might even have explained this already. Strong and weak entities. And an example of that would be employees would be a strong entity, and dependents that belong to the employee would be a weak entity. Because an employee might exist without a dependent, but we're never going to have a dependent, hopefully, who exists in the system without an employee. So hopefully you can kind of see that from that example. Very rare do we ever actually have weak entities, and sometimes people don't even actually indicate whether it's weak or strong on the diagram because it all turns into the same thing in the end. So it all gets treated the same. The reason why we look at weak entities is because they're easy to forget. It's easy to remember employees, and then as an afterthought, oh yeah, dependents for the health insurance. And then what ends up happening is instead of making it a weak entity, they make it an attribute, and they make it part of employee. It's really easy to think about an employee with dependents and say, oh yeah, but then you have to have like usually you might have more than one dependent. Are you going to put a maximum number that can be listed? And are you going to put them in the dependent in the employee table when they probably belong as a separate entity, but they're not really an entity of the system. They only belong to the employee. So that's why they're called weak, because they don't have a separate existence on their own. They're not really part of the main core diagram. They're kind of an add-on. I think of it that way. Here we have a strong entity client that states preferences as a weak entity, because we could have a client who doesn't have any preferences. And it's kind of like how you go to a website, let's say, for example, and you start filling in information, and then you want to save your preferences. You could change the color or the font or something. And some people don't change anything, and some people change everything. So it's kind of the concept of the preference as it relates to the database. We might not have an entry for every client in the preference table. So here we have a relationship called advertises with attributes. And so this is kind of a clear way of writing the diagram, actually. The dotted line gives us attributes that are associated with the relationship. Interesting concept. When we translate the tables, each one of the entities actually becomes a table. Some, but not all of the relationships do. And it's usually the multi-valued relationships that actually end up part as a table. And in this case, we're assuming we're going to have a multi-valued relationship. It's not, in practice, not such a good idea to list attributes with relationships unless you can think ahead and know that that's actually going to turn into a table. And it actually kind of breaks the rules a little bit, too. Normally, we don't have attributes associated with the relationship. But some people like to do it because they can kind of foresee into the future, and they're actually kind of thinking ahead. They're translating the tables before they even write the diagram, which is not so good in theory. But if you already know it, I don't know. If you want to break the rules, you can. There's nothing wrong about putting attributes with relationships. It's just not very common. So here we have a newspaper that advertises property for rent. We know it's going to be more than one newspaper, maybe, with more than one properties. We can kind of see, if you're looking into your crystal ball, you can kind of predict that it's going to be a multi-valued relationship. And in this case, we have a date for the advertisement. We have a cost, let's say. And these are attributes that are associated with the relationship. Not so standard, though. And I'll show you a more standard diagram in the next couple of slides. But this concept actually brings us into this concept of multiplicity and multi-valued relationships, because that's when we can put the attributes on there. And what we're really talking about is structural constraints. So it's also sometimes called multiplicity or degrees of not really degrees of relationship, but number of relationship. Cardinality is another word for it. And multiplicity is the number or the range of possible occurrences. This is the number one. This is why I probably stopped before this point. This is because it's an interesting point, and it's the number one problem that most students kind of get faced with when they first draw these diagrams. How do you represent the cardinality? How do you put the multiplicity in there? Some students just leave it out. Problem is, if you leave it out, you don't know if that's multi-valued or single-valued. If it's multiple occurrences in that relationship, it's going to turn into a table. If it's single, it's not. It turns into an attribute. So And we haven't talked about how to translate them yet, so don't worry about it if you don't understand that point at this point. But let's cover multiplicity, and we're going to get there eventually. And this will make sense in the long run. So we have the number of the range of possible occurrences of the entity that relate to single occurrences. So we represent this by sometimes referred to as business rules. So if we have a bus, and the bus has 20 seats on it, we know we can have 0 to 20 students, kids on the bus, people on the bus. So that's what's meant by the degree. So we might have 0. Will the bus still run? The bus will still operate with 0 people. Well, maybe we really want 1. Are we going to bother going from point A to point B? Actually, if we're counting transit, we will, because the bus has to go anyway, regardless of how many people are in it, because it has to. Maybe it'll pick up people as it's going through its route. But let's say the bus isn't doing that. Let's say the bus is just going from here to here. It's not going to go if there's no people, let's say. So we might put a business rule in there that says 1 or more. It says as long as we have 1 person on the bus is going to leave. Otherwise, the bus is going to wait for that 1 person to show up eventually. The schedule is going to be thrown off completely, though. So the most common degrees of relationships are binary, where we have 1 to 1. Binary relationships are generally referred to as being 1 to 1, 1 to many, or many to many. And by binary relationships, I mean one entity having a relationship with another entity. This would be students or passengers and buses. So one bus has 30, let's say, seats. So it can store 30 passengers. One bus might not leave unless it has 1 passenger. So let's take a look at some examples here. We have a staff that manages branch, and we have SG5 with 1 relationship with branch B003. We have SL21 that has a second relationship, R2. This is not an entity relationship diagram, by the way. This is just for illustrative purposes. SL21 has a relationship with B05 here. So we just have a single kind of straight line going through. We have 1 staff that doesn't have a relationship with a branch at all. Maybe the staff just got hired on, hasn't been assigned a branch yet. So how does this look on the diagram? Here's where the confusion normally runs. We have this. This is the notation I like. Some people like to go 1:1, the 2 dots, 1:1. Actually, I shouldn't. This is not really. I like to do the 1:1 because the dots. It kind of seems like a line. I don't know, it's harder to write. Colon's easier. Keyboard. So here we have a staff, and we have an attribute associated with the staff, which is a staff number. Put it for illustrative purposes. Another entity branch with a branch number next to it. A line connecting the 2 of them. Relationship type manages. The arrow's going in one direction. We know all this part already. The new part is the multiplicity. The multiplicity part says each branch is managed by 1 member of the staff. So 1 branch is managed by 1 member of the staff. That would actually kind of lead me to believe from this staff side, 1 staff manages 1 branch. And then over here, a member of the staff can manage 0 or 1 branches. So now we're talking about the branch. 0 or 1 is managed by staff. So it's actually kind of read left to right, and the multiplicity is related to the entity in question. So this one should be talking about the staff. This one should be talking about the branch. In the branch, a member of the staff, 0, can manage 0 or 1 branch. So we might not have any. We might have staff that don't manage branches. So that makes it 0. That's why I said on the bus we might have 1, we might have 0. We can actually put a number there. It can go 1:30. We only have 30 seats on the bus. Because if we know that there's a limit, there's a max, we can put the maximum number there. Here we just have nothing. We have 1, 0 or 1s that we're working with because we're having 1 to 1, kind of a binary relationship going on. And so we can actually have more than that. We can have multiple rather than a binary. When we have multiple, we have, like, for example, here, SG37. This staff member has 2 different relationships with, has overseas with 2 different relationships with property for rent 21 and property 36. This is property for rent And these are the property numbers that were assigned. And so the diagram for that looks like this. Well, now we have this asterisk in here that means more than one. It means any number. Sometimes you see an N, and this is the most confusing part of entity relationship diagramming are the symbol sets and the notation. You'll see N, M, or asterisk. It's like any number, multiple, or programmers, technical people like the asterisk, and database people like the asterisk because they're thinking, select star as a wildcard from this database. So how does this diagram read here? We have each property for rent is overseen by 0 or 1 member of the staff, 0.1 that's related to the staff who's overseeing the properties. Or over here for the property for rent, we have 0.asterisk, which means each member of the staff oversees 0 or more properties for rent. So the 0 is for the staff, oversees one or more, or many properties for rent. Are we good? That's all you need to know. You got that part, it just gets complicated from this point forward. Because we're looking at one entity with one relationship with another entity. When we start adding more entities to the relationship, that's when it starts looking a little confusing. But it's not really confusing as long as you just keep that basic notation down. That basic concept is the same. So here we have newspapers that advertise property for rent as the relationship type. So here we have advertises. One newspaper might advertise property for rent. This one we have, I don't know the names of these newspapers. I should probably change them to something like Mercury News or something. Advertises, we have two relationships with two different properties for rent. Here we have one that's got, one property for rent that's in two different newspapers. And we have we can read it left to right, right to left, and we can kind of look at the relationship a bit. And we have a many-to-many in some ways. Because we have multiplicity of the newspaper that advertises property for rent. So this is, again, another example of many-to-many. You could actually, if you wanted to, if you didn't want to specify 0 or 1, you could put an asterisk, asterisk, or asterisk colon asterisk to say many-to-many, or any number to any number. Sometimes you see m.n, many to any number. So it's just the way you want to express it. That's where the confusion normally rides. So here we have each property for rent is advertised in 0 or more papers, 0. More. Each newspaper advertises 1 or more property for rent, 1. More properties for rent. So, structural constraints. So the multiplicity are complex relationships. The number or the range is the possible number of occurrences. So these are the number of entity occurrences, if you think of it that way. So n-ary relationships with n-1 values that are fixed. So let's look at 3. So we've looked at 2, one entity that has one with another entity. Now we have the staff that registers clients at a branch. If you remember that, we have 3 participating entities. So we actually map it out kind of the same way, where we have 2 relationships here, 3 relationships here. They're all with different clients. What do we got? We have same thing as before, so don't get confused just now because we added a 3rd entity to this. We have staff that registers client at a branch. One staff goes this way to branch. Same thing we saw before. Get rid of the diamond. This is, I wish I had a hand and put it over the slide. Put your hand over client, erase it. We're just looking at the staff of the branch. It's the same thing we saw before. When we add the client in here, the client kind of goes up this way and works with both. Because the client is registering with a staff at a branch. So we have 0 clients. We don't just because we're in business doesn't necessarily mean we have clients. If we want to be successful, we're going to need clients. But doesn't necessarily mean we have them yet. So we might have 0 clients. So staff person might not have any clients, or it might have more than 1 client. And then the client is going to register with the branch through the staff. So some students like to kind of come up and put this in the middle and kind of go this way, but it's really going through the register's relationship. So when you do it, what you don't want to do is kind of go asterisk, 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 asterisk everywhere, or leave out the cardinality, because this cardinality here, this asterisk down here, is going to tell us that this relationship is multi-valued. Anytime we have an asterisk anywhere, see, if we didn't have this guy here, we would have staff that works at a branch. So we could actually take this and create one table out of it. If you put your hand over client, and you're just working with staff and branch, because it's one-to-one, only one staff works at one branch. It's kind of like student with a campus location. You're a student at IT, you're taking classes in San Jose or Sunnyvale or wherever. Hopefully you're attached to one campus, or you're in China. Or because we actually had, believe it or not, I was just thinking about this, we actually have different campus locations. We're not just here. So you might be associated with a different campus, but you usually go to one campus. So you can actually take that information and turn it into an attribute. This diagram, if you put your hand over clients and get rid of it completely, would produce one table. Because we don't have a multi-valued relationship. We have a one-to-one, one-to-one. This is one single one. So if each parent only had one dependent, not going to work. We have many dependents. We can't take in a table and have a column that represents a multi-valued attribute. It doesn't work. Otherwise we have dependent 1, dependent 2, dependent 3. And oh no, Joe's got 4. Oh no, build another column, dependent 5, dependent 6. Wrong design, wrong way of doing it. Instead you have another table. So you have two tables, one that has employees, the other one has dependents in it. And we have a key in the dependents table that says, what's Bob's employee number? He's employee number 1, he's E1. So over here we have E1, dependent number 1, E1, dependent number 2, E1, dependent number 3. All of them listed out in a separate table, all connected through the E1, which is Bob's employee number. So we connect them together. This is actually what this relationship is showing us. It's showing us how we're connecting the information that's associated with, in this example, staff and branch, but this could have very well have been employee and dependent over here. And if it's multiple, we're going to need two tables for it, long story short. Because we have client, it complicates it a little bit further, not so much, but we can actually, if this were implemented, we had 1, 2, 3, 4 tables out of that. Because we need a table to keep track of branch, table to keep track of staff, table to keep track of clients, and then the registers table. And so that's really jumping ahead, and you can probably logically see how I got there, but I'm going to show you how to get there through a formula in a few minutes. But because what we're trying to do is represent the real reality of the situation on the diagram. Take the diagram, translate it into tables, and then we don't have to think about what belongs in a table. We already know. The diagram's going to hopefully tell us. So here we have the asterisk, meaning there could be any number of client. The other thing to remember is this is talking about staff. This is talking about branches. This is talking about clients. So 0 to any number of clients would register with one staff person at one branch. One staff at one branch. One staff, one branch. So you can kind of play with the words a little bit if you want, until you can tell it sinks in if you're having problems thinking how that works. So here's here's some examples here, a summary of the ways to represent multiple constraints, and then I'm going to show you how to translate those tables. 0, 1, 0 or 1 entity occurrence. 1 means exactly 1 entity occurrence. It means no more than 1, no less than 1. 0, asterisk, 1, asterisk, 5, 10, minimum of 5 up to a maximum of 10. So you can actually kind of construe it the way you want to kind of make it make sense, give it meaning. In terms of the constructural constraints, it's what's referred to as cardinality. That's the word for it. And so multiplicity is made up of two types of constraints on the relationship, cardinality and participation. So they're actually two separate concepts, but they're treated the same way, and we'll see how that works in the next lecture, actually. But cardinality describes the maximum number of possible relationship occurrences. Participation determines whether all or only some of the entity occurrences participate. If they don't all participate, they may not necessarily turn into a separate table. So we'll have to take a look at that in a few minutes, and you'll see how that logic kind of works. So here we have multiplicity and participation constraints all put together. And in terms of participation, don't worry about it. It's nothing more than another way of representing the cardinality. So another way of thinking about it. And here's how it actually gets separated. So the cardinality for the staff versus the branch, the one-to-one. One branch is managed by one member of the staff. This is review. We've just gone over this. That would actually talk about the cardinality component. The participation is saying all branches are managed, mandatory participation of the branch, which means we have one branch has to have one staff person. We can't have a branch that doesn't have a manager. But we can have, so this is actually kind of just, well, over here we can have a staff, because we're talking about the staff who's managing branch. We could have a staff person who doesn't manage a branch. So the participation over here is not all staff manage branches, optional participation of staff. So what we're looking at is it's optional if we use a 0, and it's 1 is participation. Anything above 0 means it's a full participation. So, well, could lead to a full participation in that particular case. And on the cardinality side, one member of the staff manages one branch. So you can actually kind of look at the way that the numbers are presented, the 1:1, 1:1, figure the first one's participation, the second one's cardinality. You can think of it that way, or you can think of both concepts working together. And if you can't figure out participation, don't worry about it. It's trivial, actually. It doesn't really mean. We always assume full participation anyway. If it's possible, it's possible. We're going to put it in the design. So it's only when you want to nitpick it. In fact, let me just mention normal forms for a moment. If you want to get anything above a third normal form, you have to think about participation, actually. Because participation might actually determine a different table structure. But I haven't talked about normal forms yet, so don't worry about that either. I'll revisit participation when I talk about that. Problems with ER models, or ER modeling in general. You might think, oh, it's a straightforward science, and we're going to show you two different problems. You're going to look at that, and you're probably not going to see the problem, hopefully. If you see the problem instantly, you're a natural-born entity relationship diagram creator, and you should do this for a living. So, all right, problems that might arise are designing the conceptual data model. First one is called a connection trap. So we have connection traps that occur. And you're going to make these, you're going to actually do these, and you're going to make these problems probably in that first assignment that works with entity relationship diagramming, because it's just a natural thing to do. Often due to misinterpretation of the meaning of certain relationships. So now it's your interpretation of the facts of how you're going to put this together. So you have two main types of connection traps. There are fan traps and chasm traps. So the fan trap, the first one is where you have a model that represents a relationship between entity types, but the pathway between the certain entity occurrences that is ambiguous. So you have a branch, you have a staff that manages two branches, but you don't know which one, or something. You have the path, but it's just ambiguous. You can't tell which direction it goes in, and I'll show you an example of that. And the other trap suggests that there's an existence of relationship between two entities, but the pathway doesn't exist. Like, there should be a relationship, but there's no way of getting there. There's no path in the diagram. So let's take a look at the first one. Here's an example of a fan trap. And let me tell you, the fan traps, the number one problem is the order in which you're putting in your entities. So what ends up happening is that nobody ever wants to use the diamond, so everybody creates fan traps. Because the fan trap is going to give you that problem. Or it's going to give you the order that you just wrote them out in, because you took your entities and you drew them out first, and you start connecting them, and in the order you draw the dots is going to create the trap. That's what's going to happen. And here's because of the way you're reading the diagram. So here you have a staff that there's a division that the staff works in. The division operates at branches. The division might be students who are in majors at a campus. It's the same kind of concept. And it's not really a cardinality problem. It's the order that we have this represented in. And we have to ask ourselves a question. Oops. Oh, here we go. Back. Here we go. question we might ask is we have a branch that has a division that operates at a branch. What we've done is taken this and we've illustrated it in a kind of a different way. These are the illustrative purposes. This is not the diagrams. It's just for understanding the diagram. The staff that has a division that operates at a branch. Same thing as we were looking at before. We have staff number SG37 and staff number 9, SA9. And they have, both of them have a relationship at one division, and the division operates at a branch. And the division actually operates at two different branches. So at which branch office does staff number SG37 work at? And SG37 is up here, has a relationship with a division D1, but SA9 also has the same relationship. But this division here is operated at two different branches. We haven't really specified which branch. So it's ambiguous, which causes what's called a fan, because it fans off in too many directions. We don't have one direct path that's leading us to the correct answer. And because of that, we have to rewrite the diagram, essentially. And, oops, here we go. So we restructure the diagram. We just switch the order of two entities. So we have a division that operates at a branch that has staff. So now we have the staff connected to the branch instead of the staff connected to the division. Very, very common. Very, very common. In fact, the entity relationship diagrams that you'll have to put together will create these problems for you. I will warn you ahead of time, you're not going to like the assignment, because the assignment is going to produce ambiguous results. And you're going to look at this and go, oh my God, I've written this 5 times. How come I haven't got this right yet? That's why I say don't use them. Don't do it by hand. Because what are you going to do? Erase branch and put it over here? I guess you could erase. Do it in pencil if you're going to do it that way. And you get out 5 sheets of paper, and by your 5th revision of the diagram, you might actually have something done, hopefully. Only because you're left to interpretation. You're left to describing the instructions and what the instructions told you to do. And we'll look at an example. So restructuring the model resolves the fan trap. Now we have branch 1-to-1 operates division. 1-to-1 operates at a branch that has staff. Do we see how that works, or was that too fast? Oh, good. We're ready to move on to the next one. So we removed it. Actually, this is just an explanation going back here. So we removed it now that we have divisions that operate at branches, and we have the staff associated with the branches instead of the divisions. Problem number 2. We have a path, but we have no way of getting there. So we have a branch that has staff that oversees property for rent. Looks pretty good, actually. When you start looking at these diagrams, it looks pretty good. It's either you're tired because you don't want to look at diagrams anymore, or it's like, well, I can't see any problem with it. It looks good. I have a branch. And what ends up happening is you kind of have to go back, and in this particular example, you kind of have to think to yourself, how do I know which branch the staff works at? You know, if the divisions can work at multiple branches. So, because we have this branch with the asterisk next to it. We only have a problem when we have multiple, because now we have the option of the division being more than one branch. If we didn't have that, we wouldn't have a trap at all in here, actually. All right, so now we have this phenomenon here where we have a branch that has staff that oversees property for rent. So what does it look like when we draw it out here? We have a branch that has staff that oversees property for rent. These are the these are the components that we're working with in terms of the relationship. Branch number 3, 7, and 5 we're good so far, staff. But what staff is overseeing which property for rent? So we have to question at which branch office is property PA14 available? So now we're way over here. This property is for rent. So do we switch the order? This is when we start drawing extra lines, is what we start doing. So when we don't have the path, we actually have to put the path in. The previous example, we had confusion, we had ambiguity in the path. And so we switched the order of the entities, and it reduced the ambiguity, made things clearer. Here we have no path, so we have to put the path in. So now we have this thing here. We can actually turn that into a diamond if we wanted to. So this is the easier choice, because a lot of students can look at this and go, okay, there's no diamond, I'm cool with this. When you start putting the diamond symbol in, you start, because this is really a 3-level thing. We have to add another relationship. Here's the other relationship, offers. We could have put offers in the middle and said branch works with staff, it offers properties for rent. So we actually have this relationship. Adding the offers a relationship resolves the trap. So you might be wondering, well, okay, that's great. So now I have a perfectly running diagram. That set of entity relationship diagrams is going to produce a different set of tables than that one will. Because we're missing a relationship. In this particular case, because we have an asterisk over here, we'd be missing an entire table like this. So what ends up happening, and I do this every single time I teach this class, I give you an exam, usually, probably will be the final. I'll ask you, how many sets of tables, or take this relationship, entity relationship, translate it into tables, or take this description and create the diagram and tell me how many tables. And it'll be like a discrete number like 5 or 4. And someone will come back, oh no, I can do it in 12 or 8. It's amazing how many different number of tables can come out of that. And we'll see how to create the tables, but there really is one optimal way. And this kind of gets back into that concept of normality again, because there's different ways of building the sets of tables for the problem description. Sometimes there's duplicate data, inconsistent data, data that's not reachable, data that you can't connect to run the queries on. And it usually, if you're going through here, if you fix it in the diagram, you fix it in the tables automatically before you create the tables. So this is why you create the diagrams first, the tables second. Because the other thing that happens is I have students that come up with the table and then they create the diagram after the fact. The funny thing is when they start creating the diagram, they realize, oh, the diagram doesn't look right. Or it's because your tables aren't right. So you're supposed to create the diagram first, take the diagram, translate it into the sets of tables. How do you do that? Well, that's what we're going to look at next, actually. So to fix the problem, and that's actually simple. That's a piece of cake. Compared to creating the diagrams. Creating diagrams is the hard part. So we fixed it by adding the relationship, and when we added the relationship, we have the path created. It eliminated the non-existing path by creating the relationship. Here's some symbols. I don't like any one of these sets. If you have Smart Draw, there's different sets in the Smart Draw, actually. In fact, you're going to see different sets in the assignment that works with the first assignment that works with this as well. You're going to see, in fact, it might be a project, not really an assignment. I'll show you in a few minutes. And whatever set you use is definitely up to you. I don't really care which set you use. And here's some other component labels. And here's where I was talking about. You get the M's and the N's. And the next slide set actually has a combination of M's and N's in it, just to confuse you, or just show you that there's more options. So the relationship, different descriptions. These are just examples of what people commonly use. You want to use a relationship that's a word or 2 words. You don't want to have a whole sentence that's a relationship. And if you're going to put the relationship on there, a lot of people leave the relationship off. You just assume if you see a diamond symbol, that's a relationship. And you can use the diamond symbol without 3 or 4. You can just use it for a binary. Or you can use a line. You can't use a line with more than 2 entities participating because there's no way to connect it. Because what ends up happening is you got a line going this way, a line going this way. You got a center point. You might as well turn it into a diamond. It makes it easier, right? And it makes it less confusing. Because if you are drawing these by hand, the lines will get confusing. The lines will definitely look confusing. All right. So that's how we create, and I guarantee it, you're not going to learn everything there is to know about creating diagrams from that one lecture. It is lecture 4A if you want to download it and go through it at a slower pace. Oops. Cancel. Don't save. How's that? So don't save. So lecture 4B takes the diagrams and turns it into a table. Sets of tables, excuse me. Mapping the entity relationship diagrams to tables. This is the interesting part, and this is the really easy part, actually. So if you can get through the tables, you're great. The project number 1 is going to have you create diagrams. Project number 2 is going to have you translate the diagrams into tables. Project number 3 is going to have you take and create some SQL queries on the tables. So it's going to kind of run in that kind of a flow. So when I'm all done, I'll take a look at project number 1, and I'll show you. All right, so designing the tables. First approach, draw the diagrams. It's called dependency diagram. Sometimes people like to call entity relationship because it's kind of hard to say. Entity relationship, like ERDs. It's really a dependency diagram. It's telling you what data is dependent upon other data, essentially, because you're looking at entities that with the relationships. People don't translate that into databases. It's commonly referred to as a dependency. Each statement is a single path through the diagram. In fact, you can test your diagrams. All you have to do is reread your sentences. Say, teachers work at schools. Okay, teachers work at schools. And then make sure all the paths are there. And then you know your diagram's correct. Tables are formed by traversing the dependency diagram. Paths are hard to follow. So we create the entity relationship diagram using the dependencies. Because what students end up trying to do is they follow the paths of the dependencies without the diagram. They take and they map out in fact, some people actually write sentences and they go, students, and they make a whole list of these things and they start turning them into tables. When you do that, you end up with too many tables. You usually end up with more tables than you need, actually. Because some of the stuff can be combined in terms of the dependencies. Okay, then you transform the entities into tables, you transform the relationships into keys, and also tables, and you're done. No paths to follow. So it takes away all of the human thinking that goes into this toss a coin, toss a coin methodology. You know, read the description, toss a coin, pick some tables. All right, here's our starting point. So, like it does show up. Oh, it's in color too. That's nice. Sometimes, depending upon the projectors, it actually shows up in black and white. We're in luck. This is color-coded. This is a real entity relationship diagram. This is different than the ones you've been looking at so far because this is an example of all of the attributes in little bubbles hanging off of the entities. In fact, we have employee. All of these, what are they? Aqua green color, turquoise color. I was thinking of the color. Bubbles. Yours don't have to be turquoise. Yours don't have to be color-coded. You don't have to make bubbles. You can actually put them all in the same box if you want, like the previous example. Put employee. If you're going to do that, put employee on the top, draw a line for all the attributes underneath it. Because we want to separate the name of the attributes, the name of the entity from the list of attributes. Because then it gets confusing if you just put them all in one box and word wrap it all the way around. It just looks too confusing. Disregard the double lines here. It's supposed to be single lines. This is interesting interpretation by the projector. But it's supposed to be single lines. This is real sloppy. This is actually kind of like what I like to do. One, any number. And it doesn't mean it's wrong. There's absolutely no right or wrong way of doing this. What you're doing, it's more of an art than it is a science, actually. As long as you get the entities, some relationships, some other entities, and some notion of cardinality in here, you're good. You're good. So that's the starting point. First thing we want to do is review the constraints. We're actually going to fix the diagram first, or double check the diagram, let's say. Because what ends up happening is, you're working in a database office and someone says, somebody puts this together for you. Or draws you a picture and you make this into a diagram. It's your starting point. So you kind of review the constraints a little bit and you rework the diagram to fix the diagram. Because you definitely want to start with a good diagram. So here, an employee can work on many different departments. A department can have many different employees, which is what the constraint is actually kind of talking about here. The constraint. In contrast, each department has at most one manager, according to the key constraint on manages. Here's where the business rules are going to be imposed. This is when, in the first assignment, you're going to have to write down assumptions. So you can take a couple of different approaches to this. What usually ends up happening is you've walked into a meeting and you've given this, and all of a sudden there's a bunch of questions after you look at it. If you don't have any questions about it, then the person who did this should be writing the database tables too. So, the assumptions are going to be made. How can we have just one? Can they manage just one branch? How many buses do we have? How many people do we have? And all bunch of assumptions and questions come out of it. We're assuming that there's a relationship between us. So we're assuming that they have managers. Do they have to have a manager? So what ends up happening is you have an entire list of assumptions or inconsistencies or problems that might exist. And you fix the diagram to answer all of those questions. You also review the participation constraints and make sure you actually have participating entities. So does every employee work in a department? If so, that would be a full participation, and that would be a participation constraint, which means every employee must have a department number. So participation gives us uniqueness, gives us keys, gives us information that we're going to want to put in as a constraint on the database. We talked about constraints already. Constraints is it's required. It has to be unique. In this case, it doesn't have to be unique. All the department numbers are hopefully going to be the same, so we can tie them up. But we know we're going to have to make something unique. So then basically it means at least one in terms of the participation. Each employee has to have at least one department number. Does he have more than one? We fixed the cardinality with that as well. We identify the weak entities. Usually at this point you actually have to create the weak entities. Because what ends up happening is you're going to be stuck with a diagram that's going to have employees with dependents off of it as an attribute. So we take and we create any weak entities. Weak entities are kind of funny because they're hidden. They're hidden attributes. And they turn into weak entities because we have to make them into weak entities. The average person isn't going to do it for us in terms of what we see. Or maybe the diagram already has it, so we can go ahead and work with it. Maybe there might not be any in there at all. So the weak entity can be identified uniquely by considering the primary key of the owner's entity. So we start looking at the relationship of that and say, well, employees have a policy. The policy has dependents on it. This would be like for a health insurance policy. Weak entities have only a partial kind of key to it, maybe sometimes a dashed line. So we can actually take the diagram in this particular case and underline things, color code things. You don't actually have to. I see people put their entire database table structure into the diagram. And then I have people that don't do that at all. I personally don't like it. I don't like putting all that keys and stuff in there. But the more you do that, the more you actually have told the reader who's going to implement this that I want that to be a key. I want that to be something. Sometimes it's right, sometimes it's wrong. Sometimes you have multiple. You don't want to have more than one primary key in a table. Sometimes weird things happen. Then you review the relationships, which is the other thing that can go wrong. Basically what we're trying to do is fix all the problems in the table. So in terms of this relationship, if each policy is owned by just one employee, we've got a bad design versus a better design. So up here we have the bad design. Down here we have the better design because we've restructured it. We said the key constraint on policies would mean that policy can only cover one dependent. So we have the policy here now with, here policy number cost. We've moved the policy number around a little bit. I don't know, don't worry about what changed, but think about the relationships, restructure the diagram to account for all of the relationships, review them. In the previous example, we move things around. So we have, let's say this one here versus this one here. We might have one that's a little better. In fact, this is nice looking. That's sloppy. We have a relationship here. This is what happens when you don't draw it like that. If at a quick glance, these might look like an entity, even other relationships. And it's kind of going in a circle, which is kind of weird. So S can, and it reads differently. S can supply P, D needs P, and D deals with S. Does not imply that D has an agreement to buy from S and P. So in terms of the business logic, you can kind of review the relationship, restructure it. Sometimes it actually helps to take the diagram and divide it out into different parts. Whether you have 5 diagrams or whether you have 1, it still translates into the same number of tables. Theoretically. You should definitely have the same results. So here's our ending point, and actually, believe it or not, this started out good. We didn't have to make any changes to it. So we went through that process for nothing, outside of illustration points. So, step number 1, take all of the entities and turn them into tables. So each entity becomes a table. So, and then the entity and the table name can actually be the same for the most part. And in the primary keys, we pull one attribute out of each one of the entities. So we have employee, department, and project in here. In fact, you can actually do this. You can write this out. You don't have to put it into a table. Actually, I just like write a list. I just take the diagram and I'd list out all the entities. And then I actually skip ahead. Instead of doing the last with the weeks, I'll do the weeks next to. So you can take all the weak and all the strong. They all turn into tables. And then I'll pick out a primary key for each one of the entities. Because we want to be able, once we just flatten, because what we're doing is taking this diagram and flattening it out. Once we flatten it all out, we've got to put it back together. And we put it back together with the SQL. So the unique primary keys for each table is going to tell us how to identify, how to put it back together. And then we look at the relationships next, because that's all we have left. After we've taken all the entities out, now we have relationships. The relationships are interesting. The 1 to n, or any number, 1 to many, we put m, n, asterisk, relationships, create the primary key. Because we have to be able to tie up each one with each one. So, as an example, employee, something about the employee table, maybe the employee ID, social security number, whatever their primary key is, creates the relationship with the dependency table, and it actually becomes part of the dependent table. Which means we have to take, tells us we have to take employee number, put it in dependent table. So we transfer the information over, creates a primary key for the other table. So for each end-to-end relationship, create a primary key from the entity on the one side to the entity on the n side. This is why we need cardinality. We have to know 1 to many, 1 to any number, where it becomes a foreign key. So this is why it's a foreign and a primary. It's primary in the table that it originally belonged to. So an employee number is a primary key of the primary employee table. It's a foreign key in the dependence table because it came out of the dependence table. We knew it had to come out because of that 1 to many relationship. If we hadn't determined it to be a 1 to many, it wouldn't come out at all. In fact, it wouldn't turn in. It wouldn't create a separate table. It would be a blank table. It'd be empty. And we'll see that coming up actually as well. So N is the employee side works for one department. Here we have the department number is moved into the employee entity. So if we only have 1 to 1, we have a department number that goes in. We don't have a separate table. Why do we need a separate table for departments that employees work in if they only work in one? So we can eliminate through that relationship that's not a 1 to many, that's 1 to 1. We can actually remove that and not actually have to worry about keeping a separate table for that. Examine the weak entities, which we have already. I would have done that in step 1 actually, taken all the entities, weak or strong, created a table out of them. The dependent entity cannot exist on its own, and it must have a parent entity, employee, and it's defined by a many to any number. So many employees might have any number of employees, any many of dependents, yes. And so the entities become tables as well. So each one of the weak entities creates a table, just like the entities did. Include the primary key of the owner table. So that's different. The difference with the weak entities versus the strong entities is we don't have anything from any. All of the entities that are strong are standalone tables. All of the entities that are weak have another piece of information that's added to them. They have to have the relationship represented from the strong table. So they have an extra key in them, an extra attribute that gets added. The extra attribute is where they came from, who they belong to. So here we have the primary key that becomes the owner key plus the weak entity key. This is very popular, but can be avoided. We don't actually have to make a composite key out of it, but it's very popular. So we could take the entity dependent and the table dependent, and the primary key could be employee social security number plus the dependent number. Or we can make 2. We can make employee number, dependent number. Or this is more efficient, but people don't like composite keys. But this is how you can actually automatically create a composite key out of it without even thinking. So. And what about the many to any number of relationships? Asterisk to asterisk, M to M, N to N, however else you want to represent it. You have a separate table for it. So the multi-valued relationships always turn into a separate table. The single-valued ones don't. It's just the key that gets moved over. And all of the weeks act as single-valued relationships, actually, because they get a key as well. They pick up a piece of information. So for each of the M to N relationships, create a new table with the primary key being the primary key of both entities involved in the relationship. So here we have employees that work on projects. We have an employee number, the number of hours, the number of projects. Because employees might be working on multiple projects with multiple number of hours. How are you going to keep track of that? You can't. Otherwise, you're going to have project 1, project 2, project 3. Not a good idea. So you make a separate table out of it. So we have employee 1 is working on 2 projects, project 1, project 2 with 3 and 4 hours. So here's what it looks like, actually. And this is a simpler example. I have the main tables. This is the last slide, I think, on this lecture. This is a little bit easier, though, to understand. The names have changed, but the faces are still the same. So we have over here, this came out of a book. It's a textbook example. I can't remember which book. We have representing a many to n relationship ER diagram. All right, so what do we have here? Different symbol set. We have circles, lines, and crow's feet going on. Same kind of concept, though. These are attributes. These are entities. We have one relationship. So we have an order that has products on it, an invoice. So, and this is common, actually. People leave out the invoice. People leave out the relationship entity on this. So you'll create a table of orders and you'll create a table of products. And somehow they try to merge it together with SQL. When there's really a third table involved. It's really, because this is a multi-valued relationship demonstrating that you need 3 tables out of that. So how do the attributes work out? They become attributes of the table. So order has order date, promise date, order number. Over here we have order table, order number, order date, promise date. We have the relationship. Now this was called request. And it only had one attribute here, quantity ordered. We put that in the table, like I said before. You can. Or you can leave it out. Because what ends up happening is you start looking at these guys. You start looking at the order and you start looking at the product. And everything that you want to tie the 2 tables together with, you put in this table. So here we called it order line. We could have called it invoice, purchase order, whatever we wanted to call it. We decided on a product ID. Well, that wasn't even part of the diagram, but we put it in there anyway. And we decided on a quantity ordered. Well, that was in the diagram. Well, that's fine. But we got product ID. We needed out a product in order to take this and put it together. So another thing what you'll end up doing is you'll see the diagram and it'll be missing information. It'll have too many attributes, not enough attributes. Because here's what people do when they create the diagrams. They put everything. Address, telephone number, zip code, everything in there. And then down over here we got the employee address, telephone number, zip code, and we got the employee address. We only need it in one spot. So we figure out when we do this, we try to have one attribute, one location at a time, and use the query, use the SQL to put the tables together based upon the keys. And we only join the tables on the keys. And we know which keys to pick because if we take and look at the diagram, if we want to make the diagram out of it, that's how we're going to pick the keys. So in here what people actually try to do is simplify it. Figure you can always add attributes. Attributes are easy to add. So they'll leave a lot of the attributes out. Only put the important ones in there. I personally only like to put the keys in there. What I think is going to be a candidate for a key, I put it in there. I'll leave out all the other information. It's kind of sloppy, actually. But I'm the one creating the tables from it, so I know later I'm going to put the employee address and telephone number in the employee table instead of putting it on the diagram. So, but that's actually kind of a good simplified example. Let's take a look at the concept of the multi-value just to reiterate that point. So for each of the multi-valued attributes that we saw there, we created a new relation for it. Students don't do this for some reason. I'm not quite sure why. This is how we get fewer tables than needed. Instead, what they do is they create the multi-value and they put it in one of the tables. So the primary key is the primary key of the entity plus the multi-valued attribute. So we have department location. The table is department underscore locations. which is kind of how this turned into order products, order line, order products. People actually try to label the table that way. And the more you look at databases, the more you see this. Yeah, department locations, it's departments and locations, projects and employees, administration, registration and students, or student registration. That kind of gets put together that way. Primary key obviously is going to be the department and location, so we have 2 in 1. Essentially, is multi-valued. So here's about our n array relationships. Those n arrays create a new entity table. Entity and creates primary key of each of the entities involved in a relationship with a new. So we have suppliers that supply parts from cities. Here's the table, supplier, parts, cities. As I mentioned before, we got all 3 of them in there. And primary key is coming from all 3. So the hardest part, I guess, is trying to figure out which one should be the primary key of each one of the entities. And then knowing if you're going to represent the relationship in a table, you got to include all the primary keys of all the participating entities in the relationship. As long as you got that, you got it all. Actually, with a little practice, it turns into some pretty fancy tables. This is a combination, you'll never see this. This is that first entity relationship diagram we saw in the beginning with a table structure. It's flattened out. This is what happened. We have employee department, department locations, works on. This is the same diagram. It's flattened out. We've underlined PK. We've actually put on here PK, FK for foreign key, primary. You don't have to, actually. People, in fact, I don't even like this. This looks really sloppy. I like to list it all out. Underline. Actually, what I used to do is do an underline on the primary and a double underline on the foreign. But then you got this whole big legend on the bottom. It's single on the foreign, the color, or color code it if you want. This is where the tool sets actually come in handy. Because then they can, they'll create the legend for you and they'll have all the symbols in there. Another reason why you probably want to pick a tool set instead of doing it by hand. So I believe that's the last slide. It is the last slide. So let's take a look here, because I still have a few minutes here. No more lecture. We're done with that. So the assignments, hopefully you should be looking at. They're pretty easy. The assignments, in fact, you probably can kind of get through assignment number 3 at this point. Remember, all of these assignments do get uploaded into the ITU EMS. The links might be broken. If they're broken, send a message to the TA. We're still currently working on the problems. Some of the students don't have access. It'll say access denied or something. In fact, it says access denied for me. I can't even upload anything. So, not that I'd want to, but if I wanted to, I couldn't. So don't stress on it, but you can still work on this stuff without turning it in. You don't want to do is wait till the last minute. And what is this? The assignments, I just want to look at number 3 real quick. Select to reporting net. You probably don't want to do number 3 yet. Number 1 and number 2 are going to be covered. Yeah, number 2 is on entity relationship, just some question and answer. That one you could probably do, and it's also on SQL. And number 1 is really easy. I've gone over that one already. The one I haven't gone over yet is project number 1. Project number 1 is the first step of 3 different projects, or 4 different projects. I think there's 4 actually. Excuse me, one of them, the first one has you create the tables, the second one has you translate them, the third one has you write SQL. I can't remember what the 4th one does. Maybe it has an interface to it. They all sort of work together, but they're all different. They're going through the stages of development through some sample problems. You'll notice this one should have like 30 or something, 30 or 32 pages to it. You can't read it, it's really small writing. If you skip to the end, to the 32nd or 33rd page, you'll actually see the assignment. And as you scroll through it, stop for a second, you'll see a different symbol set used. You don't have to use the symbol set. If you're clear on entity relationship diagramming and you've got enough from that lecture, you can go back, download the lecture, and look at it again. You don't have to read this at all. Just skip to the end and answer the questions. You may use any symbol set you want, any format you want. Common perception is students that they think they have to copy this format. You don't have to do that. It's totally up to you. This is actually going to show you everything. It reads like a book, actually. There's different ways. In fact, it's not bad reading if you have the patience for it. I don't like to read, so I don't have the patience for it. If I were a student, I'd just skip to the end of it. At the end, we have questions. We have 4 different. The assignment is worth 10 points. There's 4 questions. Each one of them is worth 5 points each. So, no, is it 20 points? No, 2.5 points, I guess, if it's worth 10 points. What do we got here? Exercise number 1. I just want to kind of show you or give you an example of how to approach the problem. So, you're going to identify all of the entities, attributes, relationships. Let me see if I can make this a little bigger. 200%, how's that? Here we go. You're going to identify all the entities, attributes, relationships, types, degrees. Hence, draw an entity relationship diagram for the first one. It's talking about cars, different models of cars. What you actually have to do is kind of read through. And what I would do is kind of like, if you printed it out, or if you had a piece of scratch paper, make a list of all the entities you think might exist. Make a list of all the relationships you think might exist. And then put them all together. I know. So this one's actually, there's only like 2 different ways of doing it. And I'll tell you, this is a 3 level. This is a 3 participating, I think. Don't quote me on it. Actually, let me read it. I'll find out. An organization makes many models of cars where the model is characterized by a name and a suffix, such as GX, LX, and XL, whatever, which indicates the degree of luxury and the engine size. So we got one attribute. Excuse me. We have one entity, and it's going to be cars. And the cars has come attributes. It's going to have a name, a suffix that's associated with it. So each model is made up of parts. So we have parts that go inside of cars. Parts is going to be a separate entity. And the only way you learn this is to kind of go through practice. Just kind of think about it and break it out. And this is the thinking that hopefully you might want to be using. Each model is made up of different parts. Each part may be used in the manufacture of more than one model. So you know that there's going to be a multiple degree relationship going on. Each part is a description and an ID code. Well, that sounds like attributes. So you can actually kind of, when you list things out, you can say, part, ID, name. You can actually kind of list out the attributes that are going to be associated with it. And you can actually eliminate half of the text at that point because you can cross that out and say, okay, I've dealt with that already. Each part has a description and ID code. Each model of car is produced at just one of the firm's factories. A factory, another entity. It's going to be produced somewhere. The relationship is produced, if you want to call it that. You can call it anything you want. And we have different locations for the factories. It could be an attribute, maybe a location. And the location is going to be London, Birmingham, Bristol, Manchester, one of these locations. One in each city. What I don't want to see is, you don't want to take factory. I've seen this before, actually. You go factory 1, factory 2, factory 3, factory 4. For each one of the London, Birmingham, Bristol. No. You don't want to go car 1, car 2, car 3, for all the different models. I have had students do this before, so that's what I'm trying to tell you. Think of the entities as objects and entity occurrences. We have factories, we have cars, we have different types of cars, we have different types of factories that are in different locations. We have parts, we have different types of parts. Don't go part 1, part 2, part 3, part 4, we have parts. So think about single entities that represent, and we have different entity occurrences, and how are you going to represent the occurrences? Probably with attributes, maybe. And then some of this information is also telling you about a relationship. We have parts that are part of cars that are built in factories. And actually that's about it. So the factory produces many models of cars. So now we're looking at cardinality. Now we're looking at one factory might produce many models of car, but can cars be produced at just one? Oh, yeah, here we go. Each car is produced at just one of the firm's factories. So one, yeah. So it kind of gives you, it's trying to tell you all of the information very easily. The first one is very straightforward. The second one is not quite as straightforward because of the wording. The second one is purposely worded ambiguously. The first one, I will tell you, is very straightforward. There's only 1 or 2 different design methods. Depending upon how you like to draw, you might actually come out with. Number 2 And I'm not going to give you everything because this is really a mental exercise for you to kind of get the feel of how to do this. A university consists of several faculties, and immediately you think, faculties. What's that? It's ambiguous. Within each faculty, there are several departments. Okay, do you mean like faculty people? Do you mean like faculties, facilities? All right, so each department may run a number of courses. Okay. All teaching staff is attached to departments. Each state belongs to at least a unique department. Okay. See how many meanings you can assign to this ambiguous sentence? Which one is that? Each department may run a number of courses. All teaching staff is attached to departments. Each staff member belongs to a unique department. Every course is composed of subcourses. Well, what's a subcourse? How can a subcourse be part of a course? What in the world is a subcourse? All right. Some subcourses are part of more than one course. And staff may teach at many subcourses, and each subcourse may be taught by a member of the staff. Number of staff. Here's the point. Draw an entity relationship model for this example. Show both cardinality and optionalities. Do a keyword search on optionalities, you'll see that. It's part of participation, actually. Optional versus full participation, because this is really dealing with a lot of ambiguity. Put a question mark where the degree is uncertain, not clear in the text. Don't assume anything, rather write a list of questions you would have to find the answers to in order to complete the model. So the reason why I'm pointing this out is you're not going to be able to create a model for number 2. Number 1, you can create a model for. Number 2 is going to give you some problems. So follow the instructions. The instructions tell you it's ambiguous. Believe it or not, I have students that tell me, is this right? I don't know. You tell me. I want to know, do you know what's wrong with the description? Do you know what information is missing? Do you know what questions to ask? Where can you not form the relationship between A and B? How many degrees of the relationship are there? Can you actually figure that out? So you put question marks, long story short, it's ambiguous, so you're going to have a lot of questions to come out with. This is actually what happens. That's why I said if a customer actually gives you a description that creates a perfect, they don't need to hire you. They can just write their own. Part of it is figuring out what you need to put in the database from the description, and the description is never going to be complete. In the real world, you're never going to get a perfect description that creates a perfect set of tables that creates a perfect database. It doesn't work that way. All right, the next one, number 3 and number 4, I believe are fairly straightforward. You're also going to have problems with it. Not quite as ambiguous as number 2. Number 2 is a piece of cake. Number 2 is a work of art, as I meant to say, not a piece of cake. Number 1's a piece of cake. Number 2 is a work of art. Number 3 is you're drawing an entity relationship diagram for the following. It asks you to produce also a list of questions you would have to ask in order to complete the model. They're incomplete models, but they're actually a little bit better. Number 2 is just bad. Number 3 is going to be about the same case. Draw the model stating any... number 3 has you make assumptions. The last one is all about assumptions. The third one is incomplete. The second one is everything in the world is wrong with that. The first one is straightforward. You should be able to draw that one. Anyway, it's 32 pages of reading. It'll definitely... forget the due date. That's wrong. It's not due in July. So I forgot to take that out. I need to edit that. So. Questions on the assignments. The project. So you should be able to do project number 1. You don't have to read 32 pages. You could do a search on any words you might not know, and it'll tell you in the assignment. Draw any tool set you want. You could do it on paper if you want. Number 2, I wouldn't do by hand, I don't think. I don't know. Only because you have to erase, write, and erase. But actually, that's a pretty easy diagram. I have had people draw it out, though. and make the assumptions and put it, but don't make the assumptions. It's too much work. Just list out the questions. So. Okay, so next time I will continue with new topics, and I will talk about the midterm next time. And I think that's all for tonight, unless we have any questions. So. All right, thank you all for coming. I'll see you next week.